welcome back to the first year organic chemistry. We were studying the basic concepts of organic chemistry. In the basic concepts, we have studied the electronic effects in the previous video. Under that one, we have studied the inductive effect and electromeric effect. Now let us continue the study of this resonance effect. Resonance effect. This resonance effect is also named as the mesomeric effect. Mesomeric effect. In this resonance effect, we consider one system that is called as the conjugation. Whenever we have a multiple bond in the alternate positions, there is, for example, double bond separated by one single bond, or triple bond, double bond separated by one single bond, or two triple bonds separated by one single bond. So such a system is named as the conjugation system. Suppose you have this conjugation like a carbon-carbon double bond and single bond, double bond, like this. As long as this conjugation continues, there is a continuation of the resonance effect. Similarly, when we have a carbon-carbon double bond, along with that, if there is a lone pair on any atom like oxygen, nitrogen, etc., or halogens also, then such a system is named as the lone pair pi bond conjugation. Lone pair of electrons and pi bond electrons. Similarly, here pi bond and pi bond electrons. So, such a system in which there is a conjugation of the pi bonds or conjugation of the pi bond and lone pair, there is an interaction between such systems. Due to that one, there is a displacement of the electrons. Say for example, in case of this carbon-carbon double bond, if this electron pair shifts to this position, then automatically this electron pair will shift to this position. Or we can have the shifting of this electron pair to this carbon and this to this. In such a case, we have actually two types of structures, C double bond C, C plus, C double bond C, C minus. If this electron pair shifts in this direction. If electron pair shifts in this direction, then we will be having this C minus, C double bond C, C plus. And you remember, resonance structure, this effect, resonance effect is indicated by this type of arrow. That is a double-headed arrow. And the shifting of the electrons is indicated by the curved arrow. So, this sign indicates the resonance effect. Resonance effect. And this curved arrow indicates displacement of electron. Displacement of electrons. If you consider this one, we know that oxygen is more electronegative. That's why we have this C double bond C and with a lone pair of electrons. Then this pair of electron will shift to this position. And hence we have this carbon carrying the positive charge C double bond O, and this oxygen will carry negative charge. If this lone pair interacts with this one, then we have this lone pair shifting in this direction and this giving rise to one more structure C minus C double bond O plus. Among these, this type of interaction between the pi electrons or interaction between the pi electron and lone pair, giving rise to the distribution or displacement of the electrons, that is called as the resonance effect or mesomeric effect. So, displacement of electrons, due to interaction of pi bond electrons in conjugation, or pi bond and lone pair electrons. Same in conjugation is called resonance or mesomeric effect. Resonance or mesomeric effect. And one more thing, whatever the structures that we get, the structures obtained due to resonance are called resonance structures or canonical structures. Oh, we have to remember one point. When we indicate any such number of structures, actually any one structure will not indicate the actual structure of the particular compound or particular molecule. It is actually the hybrid of all these, not mixture, hybrid. Hybrid of all these structures is called as the resonance hybrid. The resonance hybrid will clearly explain the properties of this particular compound. Now let us consider one more example. CH2 double bond CHCl. This is actually vinyl chloride. Since this chlorine carries the lone pair of electron, this can interact with this carbon double bond. That's why we get CH2 negative charge, CH double bond Cl plus. Because of this resonance structure, the chlorine carrying the positive charge and has a double bond character with this carbon atom. That's why vinyl chloride is not easily undergoing any resonance structure. It does not undergo any nucleophilic substitution reaction. Alkyl halides undergo nucleophilic substitutions, but vinyl chloride does not undergo nucleophilic substitution. This can be explained. Less reactivity of the vinyl chloride or vinylic chlorides, any such compounds, they will not undergo any nucleophilic substitutions. Similarly, let us consider one more in case of benzene. This benzene has got 3 pi bonds. If this pi bond interacts here, double bond electron shifts to this position. So we have just observe the changes in the position of the double bonds. Assume that this is first carbon, second carbon, third, fourth, fifth, sixth, like this. If you write 1, 2, 3, 4, 5, 6. Double bond is between second and third, fourth and fifth, 1 and 6. But here it is between 1, 2, 3, 4 and 5, 6. So there is a change in the position of the double bonds due to resonance. And the actual resonance hybrid for this one can be indicated by writing a circle inside this hexagon. So these are the resonance structures and this is the resonance hybrid. Resonance structures. This is resonance hybrid. Similarly, when we write chlorobenzene, suppose you write this C6H5Cl and chlorine carrying a lone pair of electron. This lone pair of electron will shift to this position and this double bond electron will shift to this position. So it gives rise to, just observe the double bond between the carbon and chlorine of this chlorobenzene. Since this electron density is lost by the chlorine, it will carry positive charge. This carbon gets the negative charge. And these two double bonds will be present. And this will further undergo resonance in this way. So it will give rise to, again one more structure, Cl positive, double bond and this negative charge. Again this will undergo resonance to give rise to this one. It gives rise to double bond, negative charge, double bond Cl plus. And this, if further undergoes resonance, it will give rise to the original structure. So all these structures will contribute for the chlorobenzene structure. That's why they are called as the canonical structures. And because of these canonical structures or resonance structures, we observe the positive charge and double bond character between carbon and chlorine. That's why this chlorobenzene or aryl halide is again an inactive towards the nucleophilic substitutions. Okay, so these are all about the mesomeric and resonance effect. But we can use this resonance effect to explain certain facts. So, resonance effect explains low reactivity of vinylic halides and aryl halides towards SN reactions. Then this resonance structure can also be explained to explain the reactivities. Their reactivity the acidic strengths of carboxylic acids. Similarly, it can also be used to explain the basic nature of, or basic strengths also we can write. Basic nature and relative strengths. Of amines. It can also be explained to explain the acidic nature of hydrogen atom of acetylene or ethyne. Let me consider these two now. By using this resonance, how can we explain the relative strengths of bases as well as the acidic nature of the hydrogens, etc. of acetylenic compounds. Suppose you consider this methylamine CH3NH2. In the previous topic we have seen that there is a lone pair of electron on the nitrogen atom. This CH3 group will have the inductive effect, so it will be giving rise to increased electron density on the nitrogen atom. That's why this methylamine is more basic. Comparing to this ammonia, methylamine is more basic because of the inductive effect. But when we consider this benzene containing the ammonia group, NH2 group, now we can observe that this aniline is a weaker base as compared to methylamine. This is because this lone pair of electron will undergo resonance with this benzene pi electrons. That's why it will give rise to C6H5 double bond NH2 with positive charge on the nitrogen atom and negative charge here. Similarly, there are two more pi bonds. So this can undergo resonance again and this can also undergo resonance again. Like the chlorobenzene undergoing resonance. Similarly, amine group of the aniline also undergoes resonance. Because of this one, the electron density of the nitrogen atom decreases. That's why this aniline is a weaker base as compared to the aliphatic amines. So that is one point. That is basic nature and relative strengths of amines. Now if you consider this acetylene, HC triple bond CH. This pair of electron will shift to this carbon atom and this hydrogen will go out. So it will give rise to HC triple bond C with minus charge and hydrogen with positive charge. Similarly, this hydrogen can leave to give rise to C, triple bond C and H. And this carbon will carry negative charge. Now, because of this 8 electrons, the octet is complete. That's why this structure is relatively stable. That's why the hydrogen atom of the acetylene group can be released in the form of the H plus ion. That's why acetylene compounds containing the hydrogen are acidic in nature. So this is all about the resonance effect. This resonance effect we will come across in mostly aromatic compounds. Now let us see one more example for the resonance effect. CH2 double bond CH, CH double bond O. Now this oxygen is more electronegative, that's why this pair of electrons shifts to this position. This pair of electrons shifts to this position. So we have this CH2 positive, CH, double bond CH and O minus. I have taken already one more example, butadiene. CH2 double bond CH, CH double bond CH2. This is 1,3-butadiene. 1,3-butadiene. Or buta-1,3-diene. Now if you carry out the reaction with HCl, actually we expect the addition of hydrogen to one carbon and chlorine to the other carbon. But it will give rise to actually two types of products, CH3, CHCl, CH double bond CH2. According to Markovnikov's rule. This is called 1,2 addition product. But because of this resonance effect of this 1,3-butadiene, it can also give rise to 1,4 addition product. Just recall, there is a shifting of the electron density to give rise to this resonance structure. One of the carbon will carry positive charge, double bond between second and third carbon, and the other carbon atom will get negative charge. And this H plus and Cl minus will link to these two carbon atoms. So it will give rise to 1,4 addition product. So this is all about the resonance effect or mesomeric effect. Due to interaction between the conjugated system containing the pi bonds or the conjugation of the pi bond and the lone pair. As in case of this vinyl chloride, pi bond and lone pair will also undergo reaction. So that kind of effect is called as the resonance effect or mesomeric effect. Those groups or atoms which withdraw the electron density from the carbon-carbon double bond, they are called as the negative M groups, minus M groups. Those groups which push the electrons towards the carbon atom, they are called as the plus M groups. So here chlorine atom is a negative inductive group but positive mesomeric group. Remember this point. In case of the inductive effect, it is a plus I effect, plus I group, because it attracts the electron density from the carbon atom. When you consider this CH3, CH2Cl, we observe that this actually electron density shifts slightly towards the chlorine atom. So this carries a negative charge, this carries a slight positive charge. But when we have that pi bond, CH2 double bond CHCl, vinyl chloride, because of the lone pair, it will actually shift to this position. That's why it behaves as a minus M group. Similarly, amino group is actually minus inductive group. This is minus I group. This is plus M group, which pushes the electron density towards the carbon atom. Here also this NH2 group is minus I group as well as plus M group. But there are some groups which can act as both minus I as well as minus M group. So all those we will consider when we go for the substitution reactions in the aromatic systems. So that is all about the resonance effect. One more effect is there, that is actually the hyperconjugation effect, that we will see in the next video. Thank you.